Solved examples, duality. Here we shall be looking at two small examples of how to obtain the dual of a constraint optimization problem. Just a quick recap. This is the constraint optimization problem with inequality and equality constraints. This is the Lagrangian. Fx plus lambda transpose gx plus mu transpose hx. F of x is the objective function, and g of x less than equal to 0, h of x is equal to 0 are the constraints. Lambda has to be greater than equal to 0. There is no such restrictions on mu. The dual function is theta d lambda mu, which is the infimum with respect to the primal variable x of the Lagrangian, which is given by this expression. First example, it contains an equality constraint problem. Minimize f of x1, x2 equals 1 over 1 plus x1 plus 1 over 2 plus x2 subject to x1 plus x2 equals 3. This is the primal problem. The Lagrangian can be constructed now. The first two terms of the Lagrangian are from the objective function, and the third term of the Lagrangian is from the constraint, which is equivalent to x1 plus x2 minus 3 equals 0. And we have a Lagrange multiplier mu. Since this is an equality constraint, mu can have plus or minus signs. We can rearrange the terms of the Lagrangian. Taking all the terms containing x1 together, we get this 1 over 1 plus x1 plus mu x1. Then taking all the terms containing x2 together, we get 2 plus x2 plus mu x2. And then we have a third term, 3 mu in the Lagrangian. Since we will need this Lagrangian in the next slide, let's remember this. So this is the Lagrangian. Theta d is the minimum of the Lagrangian with respect to the primal variables. And since x1 and x2 have been separated out, we can carry out the minimization over the terms involving x1 and the terms involving x2 in the Lagrangian separately. Let's remember this expression for the next slide. This is the dual function, its first term, which involves minimization with respect to x1 of an argument, differentiating the argument and equating it to 0. After one step, we get x1 equals -1 plus minus square root of mu. So we can express one of the two primal variables, x1, in terms of the dual variable mu. Whence, the first term of the dual function is plus minus mu to the -½ minus mu plus minus mu to the -2/3. That's when we replace x1 with this value. Since we'll be using these expressions later, let's keep them aside. The second term of the dual function, which involves minimization with respect to x2, differentiating the argument with respect to x2 and equating it to 0, after one intermediate step, we get x2 equals -2 plus minus square root of mu. Using this value of x2 in the argument, we get the expression for the argument in terms of mu. Since we'll be using these expressions later, let's store them aside. So these are the expressions for the primal variables x1, x2 in terms of the dual variable mu that we had obtained earlier in the previous slides. And these are two terms of the dual function. Whence this is the dual function's first term. This is the second term of the dual function. Whence the dual function is plus minus 2 mu to the negative half plus minus twice mu to the negative 3 over 2 minus 6 mu. Now, observing the expressions for x1 and x2, we see that mu can only be non-negative. And we will need to remember this. Now, theta d involves maximization. That's because the original problem involved minimization. So, we have these plus minus signs. Since it involves maximization, we reject the negative signs and only keep the plus signs. Whence, x1 and x2, which also have plus minus signs there, are replaced with plus signs. So this is the final expression for theta d of mu, our dual function. And this is our constraint. Mu is greater than or equal to 0. So this is the objective function. Maximize theta d mu equals 2 mu to the minus half plus 2 mu to the minus 3 over 2 minus 6 mu, subject to mu greater than or equal to 0. This is the dual problem, and this is the primal problem. It can be shown that strong duality holds because Slater's condition is satisfied. Therefore, solving the dual and then applying these expressions, we can get the values x1 and x2, which are optimal for the primal. The advantage of solving the dual is clear. It involves only one variable mu, as opposed to two variables in the primal. This is the second example. We won't claim that the dual is easier to solve than the primal in this case. This is just a demonstration with an inequality constraint. So the problem is to minimize the objective function x squared plus 1 subject to the constraint x squared minus 6x plus 8 is less than or equal to 0. This is the expression for the Lagrangian, and after rearranging terms, we get Lx lambda mu equals 1 plus lambda x squared minus 6 lambda x plus 8 lambda plus 1, with the condition that lambda must be greater than or equal to 0 because we have an inequality constraint. Let's keep this aside for future reference. So this is the Lagrangian. Whence theta d is the minimum with respect to x of the Lagrangian. Differentiating the Lagrangian and equating it to 0, we get x equals 3 lambda over 1 plus lambda. Therefore, theta d lambda is equal to negative lambda square over 1 plus lambda plus 8 lambda plus 1. And this is how to retrieve the primal from the dual. This is the objective function for the dual. So this is the dual problem. Maximize negative lambda square over 1 plus lambda plus 8 lambda plus 1, subject to the constraint lambda is greater than or equal to 0. This is the dual problem. This was the original problem. And this relationship establishes the connection between the primal variable and the dual variable.